Welcome to day 67. You know when you're typing on your phone and it just seems to know what you're going to say next? Well, that's not magic. That's a language model. And today, we're going to pull back the curtain on how it all works.
I mean, really think about it. That little autocomplete suggestion is a tiny language model, right there, in your hand. It's constantly trying to guess the next word in your sentence. And its goal is the same as the massive models you hear about every day.
Because really, that's all a language model is doing. It's playing a prediction game. And by the end of our time here, you'll get the core intuition behind how that game is played, from the simplest methods all the way to the giants of today. So, let's get into it. So, how exactly does this prediction game work? Well, it all boils down to probability. The model's entire job is to look at a sequence of words and figure out the odds of what comes next. It's trying to find a sequence that just sounds right, like something a person would actually say or write.
Think of it like a fill-in-the-blank puzzle. You've got the sentence, and the model has to guess the most likely word for that blank space. It doesn't know the right answer. Instead, it just calculates the probability for all the words it's ever seen.
So for our sentence, it might decide there's a 9.4% chance the next words are cook soup, and maybe a much lower 3.6% chance for cower. Now, it's not just guessing. These numbers come from the model having analyzed mountains of text, learning the statistical patterns of how we all talk and...
All right, so how does it actually calculate those probabilities? Well, the first approaches were surprisingly simple. It really just came down to counting. This method is called n-grams. Just think of it as a small window that slides across a sentence looking at a sequence of n words at a time. So a 2-gram looks at pairs of words, a 3-gram looks at triplets. The model just counts, okay, how many times have I seen this word followed that word? It's a very straightforward statistical trick.
But this simple counting method runs into trouble pretty fast. It has two huge weaknesses. First, the context problem. Because its window is so small, it can't understand the broader meaning of a sentence. And second, the sparsity problem. If it's never seen a specific combination of words before, it gives that combination a probability of 0. This makes the model very brittle and leads to some pretty awkward predictions.
So to get smarter, models needed to do more than just count words. They had to actually understand the relationships between them. And this was the first huge leap forward, aimed squarely at that sparsity problem.
This is where neural networks come in. Instead of treating words like separate items, they learn to place them on a kind of map of meaning. We call these word embeddings. So words like water and juice end up close together on this map. And that's the key. Now, if the model has learned I drink a glass of water, it can infer that I drink a glass of juice is also pretty likely, just because their meanings are so close.
Okay, so that helps with the sparsity problem, with words the model hasn't seen in a specific context. But what about that other big issue, the context problem? How does a model remember what was said at the beginning of a long paragraph?
The next big innovation was the recurrent neural network, or RNN. You can think of an RNN as reading a sentence one word at a time, kind of like a person does. With each word, it updates its internal memory of what it's read so far. This lets it build up context over time. The catch? This one-word-at-a-time process is slow. You can't process a whole document at once, and that makes it really tough to train on huge amounts of data.
That slowness was a serious bottleneck. The entire field was looking for the next big thing, and in 2017, it arrived. A totally new design that didn't just make things faster, it completely changed how models understood context.
And that design is the transformer. It was a complete game changer. Unlike an RNN, a transformer looks at every single word in the sentence at the exact same time. This is huge for training speed. And the secret ingredient that lets it do this is a mechanism called self-attention.
So what is self-attention? Well, take a look at this sentence. When you see the word it, what does it refer to? The animal or the street? You and I know instantly, but the model has to figure that out mathematically. This is exactly what self-attention does. As the model processes the word it, the attention mechanism allows it to look across the whole sentence and ask, which other words here are most important for understanding this word? It learns to create a strong connection, a high attention score, between it and animal. It's like drawing a line directly between them, no matter how far apart they are.
So let's just quickly trace that path. We started with n-grams, which was basically just counting words. That evolved into RNNs, which had a kind of sequential memory but were slow, and that brought us to today's transformers, which use this idea of parallel self-attention to understand context across huge amounts of text and do it fast.
All right, so that's the theory. But where do you actually run into these models in your day-to-day life?
Well, they're pretty much everywhere. It starts with that autocomplete on your phone, but it's also the engine behind machine translation, summarizing long articles, generating code, and even figuring out if a movie review is positive or negative.
And the thing that makes all this possible today is just sheer scale. A model like GPT-3 has over 175 billion parameters. You can think of these as all the little knobs the model can tune while it learns from the internet. It's this incredible size, paired with the efficient transformer design, that really unlocks their power.
What's really spectacular is just how flexible they are. The same fundamental model can perform all these different language tasks, often without much extra training. It's become a general-purpose tool for language itself.
So, if we boil it all down to one sentence, a language model is a system that predicts the most likely next word in a sequence.
And if you remember just one thing from all this, make it this. The entire history of this field, from counting words to today's massive networks, has really been a quest to solve one problem: the context problem.
And that leaves us with a final question. We started by asking how a model predicts a word. But what becomes possible when that prediction is based on an understanding of almost everything we've ever written down? What gets unlocked then?